Hey guys, Mr. Klein here. Chapter 11, Lesson 1, brand new chapter. Building on what we talked about in terms of relative age dating, absolute age dating, and fossils. We're going to go through the history of the Earth from its very beginning up until present time. We're going to spend a lot of time talking about dinosaurs and also the age of the mammals. But first, we're going to talk about how the timescale was developed as well as Precambrian time before advanced life started really showing up on Earth. So, anyway, by the end of this lesson, you'll be able to answer the following questions. Question number 1 was, how was the geologic timescale developed? Question number 2, what are some causes of mass extinctions? And question number 3, how is evolution affected by environmental change? So let's go ahead and dive into this. Just like in history, in social studies class, you have timelines. On the left-hand side of the page is the earliest events, and as you go on and go forth, you put important events and important times and things like that until you get to the end of the event or present time. That's where you put on the far right. And scientists have that in terms, especially geologists, in terms of a geologic timeline. Okay, so geologists have constructed a history of the Earth, and we put it all together in one big geologic timeline. Now, there are 4 units of time in geologic time. They go from big chunks of time all the way down to the smaller ones. And so the longest units of geologic time are what we call eons. The geologic time scale contains 4 eons, which when we look at the time scale, I'll show you them in a minute. But just for the record, they're the Hadean, the Archean, the Proterozoic, the Proterozoic, and the Phanerozoic era. Okay? Now, eons themselves are subdivided into smaller units of time of what we call eras. And these eras are subdivided into periods, and these periods are subdivided into epochs. Yes, like it was epic. That's it's a homophone. It's a word. It sounds the same, but has a different spelling and different meaning. Okay, think of it this way in these 4 geologic time units. Think of eons as days. Okay, and days are divided into smaller units of time called hours, which would be kind of like the eras. Hours are divided into minutes, which are the periods, and the minutes are divided into seconds in terms of epochs. So, eon, era, period, epoch, just like day, hour, minute, second. Okay, so there you go. So let's look at the geologic timeline. Okay, so here you go. Okay, so we have Hadean, Archean, Proterozoic, and Phanerozoic era, and then this is divided into eras. Okay, the Paleozoic, Mesozoic, Cenozoic. Okay, these eras are divided into periods. Okay, Paleogene, Neogene, Quaternary, and divided into epochs: Pleistocene, Holocene. We live in the Holocene epoch. Now, when we talk about the time, 4.5 billion years, how long is it? It sounds like a lot, but how much is it? Well, if we look at the timeline like this, and if we were to put this into a scale model where 1 millimeter would equivalent to 1 year, your timeline would stretch over 4,500 kilometers, which is about 3,000 miles. Essentially, the timeline of Earth would stretch from California at the Pacific Ocean all the way to Virginia and the Atlantic Ocean. So essentially, the width of the United States would be the geologic timeline of Earth. Okay, that sounds pretty big. Now, how do our lives fit in? Well, think about this. If you're an 8th grader, you're either 13 or 14 years old. Okay, so based on the same scale, your life would be 14 millimeters in length, so 1.4 centimeters. Okay, how long is 1.4 centimeters? About 1/2 of an inch. So how much of your life is in comparison to the entire history of the Earth based on our dating methods? Apparently, not very much at all. 1/2 of an inch is in comparison to the entire width of the United States. That's pretty small, pretty insignificant. Now, of course, we can go into even further detail as this completely complicated looking geologic timescale. We have Precambrian time, okay, and then see we have age, let's see, we have the period, we have the epoch, these are the eras, okay, period, epoch, age, and then the timelines of them themselves, and even right here about magnetic polarity based on the magnetic poles flipping. This is from the North American Geological Society of America during their decade of North American geology. Anyway, so needless to say, we can divide time up into really small times. Okay, so how were we able to figure this out? Well, mainly we began piecing it together based on the fossils in different rock layers. So essentially, the geologic timescale was kind of put together by relative age dating. We knew that the further down you go, the older the rocks are, and only through radiometric dating were we able to come up with absolute ages. And actually, absolute age dating's only been around for about 60, 70 years. So what we know about geologic history in terms of exact ages has only been a relatively recent phenomenon. Okay, and like I was just talking about with relative age dating, we found that older rock layers contain only fossils of smaller, relatively simple life forms. Okay, and they were at the bottom of the geologic columns. However, younger rock layers, or they were rock layers closer to the surface, usually contain fossils of simple life forms as well as fossils of more complex life forms. Okay, so it's showing that life diversified and became more and more different types, plants, animals, fungus, bacteria, archaea, okay, all that stuff. And so looking at the fossils, we determined that as time went on, evidently life got more and more complex. Okay, and evidently the Earth was really, really old because there were so many different rock layers. And this is where the relationship of the fossil record to geologic timeline is. Okay, as we looked at the fossils, we saw as the younger in time it got, we found simple to complex in terms of evolution. Okay, and then whenever we looked at the rock strata, we saw that the layers of rock at the very bottom had the simplest life forms, and then as you moved up each layer, the fossils became more and more complex. So when we put these together, the correlation was that under relative time, we didn't know the exact time until absolute age dating came along, but we figured that as time went on, organisms became more and more complex. And as a result, they lived later on, and so they were in rock strata that was higher up. Because you remember the principle of superposition says that the lower it is, the older it is, the higher it is, the younger it is on the rock strata. So, okay, now that establishes how the geologic timeline took place. But what triggered the actual evolution of these organisms? Well, essentially, what happens is mass extinctions would take place that were mainly major triggers in the evolutionary timeline. Mass extinctions are extinctions of many species on Earth within a short period of time. Now, when we talk about short period of time, we're not talking about, a month, a year. Remember, because we're talking about that geologic timeline. The distance from California to Virginia is the history of the Earth. Our life is only like at our case, the oldest person may be a couple of inches. Okay, so when we talk about short period of time, we're talking about a couple thousand, tens of thousands, even to millions of years. Okay, so there are all sorts of theories and there are all sorts of mass extinction events which we're pretty sure about. But one reason for extinctions is the quick changes to the environment when some organisms cannot adapt. For example, when we talk about one mass extinction at 65 million years ago that ended the Mesozoic era, okay, what essentially happened was all the dinosaurs couldn't adapt and they all died out, okay, because it's for reasons which I'm about to go into, is that essentially a meteor hit the Earth, okay, large amounts of dust and stuff were put into the air, okay, skies got really dark, which means it got really cold, which means it snowed, which means that the dinosaurs couldn't cope with the cold weather because the plants died because they weren't exposed to the sun. Dinosaurs couldn't eat, they got cold, they froze to death, they died, who were left? The organisms that could adapt, which means they had warm blood, they had fur, mammals. Okay, so some scientists hypothesize that the mass extinction of dinosaurs was caused by a meteor impact. And having said that, let's hop on Google Earth for a minute and let's look. Here we are at school, and essentially, okay, there's a crater which you can't see, but scientists discovered it. Actually, oil field workers discovered it off the Yucatan Peninsula. It's in this general vicinity. In fact, if I zoom out, you see where our class is here in South Louisiana. Here's the crater. Okay, it's not too far from us. Now, how did scientists figure this out? Well, evidence of the collision is provided by rocks containing the element iridium, which is really rare on Earth, but in meteors, it's full of it. And what they have, what's called, is the the KPG line in the rock layers, and there's a very thin layer, okay, that divides the Mesozoic era with another, the more recent era, the Holocene era, and essentially in that thin layer of rock, which means it was really short on the geologic timeline, there's a lot of iridium in it, okay, and so let's look at, okay, the Chicxulub crater. Okay, the buried crater is about this size in the Yucatan Peninsula, like I showed you. So it's pretty big. Okay, and here's the exact impact, which is just off the coast. And since it was 65 million years ago, a lot of rock has covered it over. However, uh, evidence of rocks pulled up in boring and drilling for oil showed that it looked like there was some sort of impact, and scientists began studying and studying and studying. And for example, what you have on the right here is a gravity map. Okay, it shows the layers of gravity, and as you can see, here's the coast of the Yucatan, and it's this right here. And what do you notice? A giant hole in the ground, okay, going down over 2 kilometers and about 20 kilometers across. Okay, so that's a huge hole. That's what, 12, 13 miles across, okay, over, over 3 miles deep, okay, is the size of the crater. So that big of a crater throwing out that much dust and stuff would have caused massive global climate change, which would have killed off tens of hundreds and thousands of different species, okay, causing radical changes on there. Now, in the past, which we'll look at other extinction events, they could have been caused based on gas and dust being released from massive volcanic eruptions. And in fact, the biggest extinction event of all time, which is right here, at the end of the Permian and the Triassic era, right here, pretty much about 96% of all marine life, in other words, all ocean-going organisms died, and over 70% of land-based organisms died in the Permian Triassic event. Okay, so that's the biggest extinction event. And then here's some other ones in the Cambrian time, an Ordovician time right here, probably caused by a meteor strike here. But right here, it's hypothesized that the Permian Triassic event might have been caused by massive volcanic eruptions all over the world. And so much gas and so much dust was pumped into the environment that the climate changed radically, and that's why you had so much death. And as you can see right here, about 65 million years ago, is the end of the Cretaceous period, which is the end of the Mesozoic era and the beginning of the Paleogenic era. Okay, I'm sorry, the Paleogenic period. So there you go. That's levels of extinction events, okay, going on throughout time. Now, going back to last year and talking about natural selection, we know that evolution is the change in species over time as organisms adapt to their environments. Natural selection states that the organisms which are best suited to survive will be the ones who can adapt to best. Now, in addition to this, the slow movement of Earth's tectonic plates can affect evolution too. So it's not just massive, catastrophes that cause this. It's not catastrophism, but also uniformitarianism. The geologic forces are taking place at slow rates. For example, when tectonic plates move, sea levels can drop, forming land bridges, which connect continents that have been separated by water. And the most famous land bridge we're talking about, if we zoom out of Earth, okay, and we go and we look right here, is what we call the Bering Land Bridge. And the Bering Strait, okay, connects Russia and Alaska. And this is really, really close, okay? Just for the instance, from here to here is only 81 kilometers or 50 miles. So Russia and Alaska are only separated by about 50 miles. And during previous eras of geologic time, this area was actually connected by a land bridge because, as you can see, the continental shelf, which is this really shallow area, the sea levels went down and this was exposed land. So in other words, Asia and North America were connected. And organisms and even people migrated across, and they came down here and they eventually settled all of North and South America. Okay, so the Bering Land Bridge is an important concept in evolution because organisms were able to transfer from one way to the other. Because whenever we look at the Cenozoic era and we look at Ice Age and stuff like that, that you had mammoths, like seen right here, or mastodons in addition, or saber-toothed cats, or dire wolves, or lions, or bears, that all these that look just like their old world counterparts like you might see in Asia or Africa, but they were around in North America. And eventually climate change and stuff happened and they all died off. So like I just said, land bridges allow organisms to move into new areas with new environments, and then they would have to adapt to them. Now, the term geographic isolation is the separation of a population of organisms from the rest of its species because of a physical barrier. So, for example, climate change happens, sea levels go up, lions are separated. Okay, there are North American lions, and then there were European, Asian lions, and stuff like that. Okay, so those were separated, and as a result of their separation over time, they'll evolve differently. Now, according to the theory of evolution, that you have common ancestors. Okay, that's one theory, and another theory is that even that when organisms go into different biomes, they adapt and fill in certain ecological niches or certain ecological roles. Take, for instance, the African wild dog and the thylacine, or the Tasmanian tiger. Okay, these are actually not related at all. Okay, wild dog is a canine, not quite related to dogs, but it's a distant relative. The thylacine, however, is most closely related to a kangaroo. Now, if we go back in the evolutionary tree far enough, they will have a common mammalian or a mammal ancestor. Okay, but the African wild dog, of course, is in Africa. The thylacine was in Australia, and because they had similar ecological niches, if you look at their bodies and look at their shapes, what do you notice about them? They have broadly similar features. You notice their faces are kind of the same, and they were both predators and they preyed on small animals. Okay, and thylacine sometimes ran in packs, sometimes they ran individually. African wild dogs have pack mentality, and they don't operate alone. Okay, so because of geographic isolation, Australia was way off from everywhere else. You had a lot of different adaptations, and because Australia was moved off, isolated long ago, the common ancestor where it breaks off allowed for radically different evolutionary changes to take place. So that's why you have a thylacine as compared to wild dogs. In fact, dogs weren't even on Australia until until people started showing up, and then you ended up having the dingo. Okay, so there's your lesson. Okay, geologic history of the Earth, uh, which will wrap up right here with the beginning of time of organisms, in essentially Precambrian time. In Precambrian time, early geologists hypothesized that multicellular organisms first evolved in the Cambrian period, which will bounce up right here. Okay, the Cambrian period is only about 540 million years ago. Okay, so that's usually when we think of when life starts kickstarting. Now, time before Cambrian was what we call Precambrian time. Okay, so essentially from 4.5 billion years ago up until 540 million years ago, there's essentially life. If it wasn't here, it was only in, cellular, single-celled organisms. We call that Precambrian time. That's when a lot of meteors happen. A Mars-sized planetoid skimmed off of Earth, probably formed the moon, things like that. When we talk about the formation of the solar system, we'll get into that. Okay, so a lot of major geologic changes were taking place. And most of the multicellular organisms that lived during the Precambrian became extinct at the end of the Precambrian period. Okay, climate change, meteor impacts, stuff like that caused that. However, Precambrian life led to a sudden appearance of new types of multicellular organisms and what we know as the Cambrian explosion. Essentially, what happened is if we look at the fossil record, we just have little multicellular organisms, little plants, protoplants, things like that. All of a sudden, 540 million years ago, bang! Okay? Uh, Everywhere, life everywhere, in all sorts, plants, invertebrates, animals, all that was the Cambrian explosion. And these new organisms are more easily preserved as fossils because they had hard body parts. Like, if, for example, you remember the trilobite at the museum. That's that little crab-looking thing. Okay, they had a hard exoskeleton, which means when they were buried quickly during disasters and things like that, they were able for them to be fossilized. Okay, so in terms of the geologic timeline, we've covered We covered about 4 billion years. Precambrian time only makes up about 4 billion years. Okay, and so what we did is we started talking about the Cambrian explosion, and we're going to move through here over each lesson, especially sitting on the Paleozoic, we're going to sit on the Mesozoic, and we'll go on the Cenozoic. Okay, so let's wrap up this lesson. So how was the geologic timescale developed? Well, scientists developed the geologic timescale through the relative age dating of rocks as well as the examination of fossil record. What we saw was the older the rocks were in the geologic column, the more simple the organisms. And so putting two and two together, we figured that as life evolved on the planet as time went on. And only through absolute age dating methods were we actually able to pin down the ages of these rocks. Now, what are some causes of mass extinction? Well, mass extinctions were most probably caused by changes in climate due to catastrophes such as meteor strikes or large-scale volcanic eruptions. Huge meteor hits the Earth, creates a huge crater, causes huge global climate change, lots of things die off. Or large-scale volcanic eruptions, which ended at the Permian-Triassic era. Okay, right here, that was when 96% of all marine life and 70% of all land-based life was killed in a relatively short period. Or at the end of the Mesozoic era when the meteor hit in Mexico, off the Yucatan Peninsula, right near us in Louisiana, it killed off the dinosaurs. Now, how is evolution affected by environmental change? Well, what can happen is climate change will kill off organisms that can't adapt fast enough, but also slower what we call under uniformitarianism, those geologic processes cause other things, like, for example, geologic isolation. It allows species of organisms to adapt to different surroundings, leading to branches of the evolutionary process. And especially if you go far back enough, you'll end up have radically different organisms like you saw in Australia and in Africa, but they still feel the same geologic niches, and they kind of look like each other. So, that's your lesson, Chapter 11, Lesson 1. Okay, geologic history and the evolution of life. Make sure you have your notes taken down. If you have any questions, feel free to let you know. And next time we'll start talking about dinosaurs. Talk to you later.